In this video, we will talk about clustering, and I want to carry one picture with us the whole way through. Imagine a classroom full of students and no teacher. Nobody hands out groups. Yet, left alone, the students drift into study circles. The ones who are alike end up together. That self organizing is exactly what clustering does. The contrast with supervised learning is sharp. There, every student would arrive already labeled topper, average, backbencher, and the algorithm just learns to copy the label. In clustering, the labels are gone. We are handed only the students and must discover the circles ourselves. Each student is a data point, one observation. Each subject is a variable, a feature, one dimension. A student's mark sheet across all subjects is their feature vector, their coordinates in space. A study circle is a cluster, and two students are alike when their feature vectors sit close together, which puts the entire video inside one word close. It means nothing until we choose a formula for the distance between two feature vectors, and that choice quietly decides who lands in which cluster. So, everything ahead is really one question. Given two students, how far apart are they? Let us build the measurement with real numbers on the board. First, what is a distance? It is a rule that takes two data points and returns one number, obeying a little common sense. It is 0 only when the two feature vectors are identical. It gives the same answer either way round. And a detour through a third point is never shorter than going direct. Any rule keeping those promises is a valid distance, and more than one does. The one you know from school is Euclidean distance, the straight line gap as the crow flies between the 2 points. It is just Pythagoras. Take students A and B on two subjects. A has maths 72, physics 68. B has maths 75, physics 72. Two variables mean two dimensions. So we plot them and drop a right angle triangle. The maths gap is 3, the physics gap is 4, and the straight line distance is the hypotenuse. The square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. Now, the step that matters, add a subject, say chemistry, and notice what that means statistically. We are not adding a subject, we are adding a dimension, a new variable measured on each point. A scored 80 and B scored 92, a gap of 12. We do not start over. We just slide the new squared gap under the same root. 3 squared plus 4 squared plus 12 squared is 169, whose root is 13. Two dimensions set 5. The third pushes A and B to 13 apart. That is the whole pattern for any number of variables. Take the gap in each dimension, square it, sum across all dimensions, and take one square root at the end. The operations square, sum, root is the L2 norm of the difference. So Euclidean distance is simply the L2 norm of feature vector A minus feature vector B, and when you hear L2, picture a straight line measured by Pythagoras. One shape to keep because we will contrast it soon. The set of points at equal Euclidean distance from a given point is a circle, a sphere in 3 dimensions. Equal Euclidean distance is a perfectly round shell. The straight line is not the only honest ruler. Sometimes it makes more sense to go one variable at a time. Add up how far apart the 2 points are in each dimension and never mix them. That is Manhattan distance. Instead of squaring the gaps, we add their plane sizes. For A and B on two subjects, that is the absolute value of 3 plus the absolute value of 4 equals 7. Across all three subjects, it is 3 plus 4 plus 12, 19. No squares, no root. This running total of absolute gaps is the L1 norm of the difference. It is nicknamed Manhattan or city block distance because, like walking a city grid, you cannot cut diagonally. You add the blocks along each street. That city image is the only aside we will borrow. The students stay a real story, and the two rulers disagree. The very same pair, A and B, on two subjects is 5 apart by Euclidean and 7 by Manhattan. Neither is wrong. They answer different questions. Manhattan has one useful habit. Because it never squares anything, a single wild variable, one student who bombed one test, contributes only its plain size and not its square. So L1 is more forgiving of a lone outlier. The geometry changes too. Points that equal Manhattan distance from a center do not trace a circle, they trace a diamond, a square balanced on its corner. Now, the mathematics that unites them, which is the real point of the scene. Euclidean and Manhattan are two settings of one formula. Take the gap in each dimension, raise it to the power p, sum, then take the pth root. That is the Minkowski distance, and p is a dial. At p equal to 1, the powers vanish and you get Manhattan. At p equal to 2, squares and a square root give Euclidean. As p runs to infinity, the single largest gap dominates, giving the Chebyshev distance. One dial, a whole family of rulers, and setting it is choosing the geometry your clusters form in. Now, the most interesting case, and the classroom makes it obvious. Student X is a topper, maths 90, physics 45. Student Y is struggling, maths 30 and physics 15. In raw marks, they look nothing alike. But look at the shape of each feature vector. Both are exactly twice as strong in maths as in physics. Same academic profile, same lean, only the overall level differs. Each ruler so far would call them far apart because they measure gaps in raw marks. Euclidean between them is the square root of 60 squared plus 30 squared, about 67 enormous. Yet, as types, they are the same. To capture that, we stop measuring the length of the feature vector and measure its direction. And the mathematics is already inside the dot product. Its geometric definition says the dot product of two vectors equals the length of the first times the length of the second times the cosine of the angle between them. Rearrange for that cosine and cosine similarity falls out. The dot product of x and y divided by the product of their lengths. Dividing by the two lengths deliberately cancels the overall level and keeps only the direction, the lean of the profile. Run it on x and y and the numbers are clean. The dot product comes to 3375 and the product of the two lengths comes to the same 3375. So the cosine is exactly 1, an angle of 0. As types identical even though one sits far above the other. Because it is a cosine, it always lands between minus 1 and 1. 1 is the same direction, 0 is at right angles with nothing shared, minus 1 is opposite. For a middle value, bring in student Z, who flips the lean. Maths 45, physics 90. Z's cosine with x is not 0.8, an angle of about 37 degrees, related but a clearly different profile. This is why cosine is the default when you care about type rather than level. For text, for documents, for the high dimensional embeddings inside language models. Point the same way and the cosine calls you alike, no matter your size. Now here is the twist that explains why cosine was ever needed. So far we compared students on 2 or 3 subjects. Suppose we get greedy and score them on hundreds of tiny variables, every quiz, attendance, even handwriting. More features would mean sharper clusters. Astonishingly, the opposite happens. This is the curse of dimensionality. The mathematics is clean. Squared Euclidean distance is a sum with one term per dimension. Pile on dimensions and that sum has more terms. So the typical distance between 2 points grows in proportion to the number of dimensions d. But the spread around that typical value grows only like the square root of d. Divide the two and the relative variation shrinks like 1 over the square root of d. In plain words, as the number of variable climbs, every pair of points drifts toward the same distance. They collapse is easy to see in number. For each point, compare its nearest neighbor with its farthest as a fraction of the nearest. With 2 dimensions, that fraction is about 25, plenty of contrast. With 10, it falls below 2. With 100, about zero point 0.3, and 1,000 dimensions near 0.09. The gap between nearest and farthest has all but vanished. And that is fatal for clustering, which lives entirely on near versus far. My cluster is near, the others are far. If everyone is roughly equally far from everyone, near and far stop carrying information and the clusters dissolve into fog. The Euclidean ruler still returns number, they just no longer separate anybody. Now, this is where cosine earns its place. It discards magnitude, the very thing that concentrates and reads only direction, which stays informative. 2 points can still lean clearly different ways long after their raw distances have blurred. Direction survives in high dimensions where distance does not. Euclidean is not bad. It is superb in the low dimensional world it was built for. The right ruler simply depends on how many dimensions you are standing in. Everything so far aimed at one final question. Once the points are sorted into clusters, is a given point actually in the right one? The standard answer, the silhouette, uses nothing but the distances we have been building. Take one data point, call it point I, and ask 2 questions. First, how well does it fit its own cluster? Average its distance to every other member of that cluster and call it A, the mean intra-cluster distance. If its gaps to the 3 others are 1, 2, and 3, then A is true. Small a means it sits comfortably amongst its own kind. Second, how tempting is the nearest rival cluster? Average the distance from point I to all the members of the closest other cluster and call it B, the mean nearest cluster distance. If those gaps are 9, 10, and 11, then B is 10. Large B means the nearest rival is safely far. Now combine them. The silhouette is B minus A over whichever is larger. Here that is 10 minus 2 over 10, 0.8 near the best possible one. The point clearly belongs. Flip it, a point whose own cluster average is 8 but whose nearest rival averages only 3 scores, 3 minus 8 over 8 minus 0.625. A negative silhouette is a red flag. The point is closer to the neighbors than to home and was probably placed wrong. And here is the whole video in one sentence. Both A and B are just distances, averaged distances between points. So the ruler you choose at the very start, Euclidean or Manhattan or cosine, is the ruler compounding every one of them. The geometry was never a warm-up. It is what the final score is silently made of. Change the ruler and you change A. You change B and you can change the verdict on every point. So the one idea to carry away. Clustering has no teacher, only a set of data points and a ruler. The algorithm never sees toppers or backbenchers. It sees feature vectors and the distances between them. And every cluster it finds through that ruler. Which means the decision that matters most is not which algorithm to run. It is one quiet question asked of your data: what should close mean here? The straight line gap, the variable by variable total, or the shape of the profile? Answer that honestly, remembering that once you measure on 1,000 dimensions, the ordinary ruler goes nearly blind and the right clusters will show themselves.